inside a rock at the bottom of a dried-up Martian lake. NASA's Curiosity rover found something that stopped scientists cold: organic molecules that have no business being there. Not just any molecules, the most diverse collection of organic chemistry ever detected on the red planet. Molecules that, back on Earth, we typically see in only one context: living things. So what exactly did Curiosity find? And why does it shake everything we thought we knew about Mars? To understand why this discovery matters, you need to understand one thing about Mars. It is hostile to chemistry. The surface is bombarded by ultraviolet radiation and cosmic rays around the clock. Mars has no global magnetic field to deflect charged particles from space, and the soil itself is loaded with chemicals called perchlorates, powerful oxidizers that destroy organic molecules on contact. For decades, scientists assumed that even if Mars had once possessed organic molecules, they would have been shredded long ago, burned down to nothing by radiation and reactive chemistry. The surface of Mars, the thinking went, was essentially a giant self-sterilizing laboratory, engineered by physics to erase the building blocks of life. And yet, in 2020, Curiosity was driving through a region called Gale Crater, an ancient lake bed that formed roughly 3.5 billion years ago. The rover reached a rock formation that looked different. Older sediment, the kind that had been buried for eons, shielded from the radiation above by meters of overlying rock. The rover drilled into it, collected a fine powder, and delivered it to a laboratory the size of a shoebox, sitting right there on the rover itself. That lab is called SAM, the Sample Analysis at Mars Instrument, and what it found, nobody was fully prepared for. SAM is extraordinary. It heats rock samples to over 800 degrees Celsius and reads the chemical gases that boil off. It can identify molecules at incredibly small concentrations, the equivalent of finding a single grain of salt dissolved in 1 billion gallons of water. Scientists had used SAM to detect organics on Mars before. Simple stuff. Short carbon chains, basic molecules. But the results from this particular sample were different in kind, not just in degree. The data came back showing a suite of organic molecules, complex compounds that included aromatic hydrocarbons, nitrogen-bearing organics, and sulfur-containing compounds, all present in the same sample, all at the same time. To put that in perspective, on Earth, when you find that specific combination of organic chemistry together in one place, it usually means one of two things. Either you're looking at the remnants of ancient biological activity, or you're looking at chemistry produced under very specific and very narrow environmental conditions. Mars supposedly offers neither, but here is where the story deepens. Because the team did not just run standard laboratory analysis. They fed the SAM spectral data into a machine learning model, an AI trained to detect molecular signatures buried inside complex chemical mixtures, the kind of faint overlapping signals that can drown each other out in raw spectral data, making them invisible to standard pipelines. The AI flagged several compounds the conventional analysis nearly missed, signatures so faint and so tangled with other readings that human analysts would likely have dismissed them as noise. The AI did not dismiss them. It found a pattern, a chemical fingerprint, and that fingerprint matched something the researchers recognized from a very particular kind of chemistry. Now, let's be clear about one thing. Finding organic molecules on Mars does not automatically mean you have found evidence of life. The word organic in chemistry simply means molecules built around carbon. Meteorites deliver organic molecules to planetary surfaces constantly. Geological processes can produce complex organics without any biology involved whatsoever. But the type of molecules found here, the specific combination, and the ratios in which they appeared, that is what made the scientists pause. If this kind of deep dive science is exactly what you came here for, hit subscribe. We go this deep every single week, and the next video will be worth it. Before we get to what these molecules might actually mean, you need to understand why this rock was different from every other rock Curiosity has ever drilled. Because location in planetary science is everything. Gale Crater was not chosen at random. Scientists selected it because orbital satellite data showed extensive clay mineral deposits. Clay that only forms in the presence of liquid water, not just any water. Neutral pH water. the kind that on Earth is considered ideal for microbial life. Not corrosive acid, not caustic alkali, just water. The rock. Curiosity drilled came from the deepest, oldest accessible sediment layer in the entire crater. Material deposited when the lake was still active, and then buried. Buried deep enough that cosmic radiation could not reach it across billions of years. That word is key, shielded. If organic molecules were going to survive anywhere on Mars, this is where they would survive. Not on the surface, not in the topsoil, but down in ancient lakebed sediment, locked inside rock, protected by meters of overlying material from the radiation above. And that is exactly where curiosity found them. The abundance, the diversity, the state of preservation. Scientists describe the sample as unprecedented, the most organically rich Martian material ever analyzed, by a significant margin. So now comes the question that everyone wants answered. What does this mean? Three competing explanations are on the table. Each has serious scientific support. None can be fully ruled out, and one of them would change the course of human history. Theory 1. Ancient geological chemistry. Mars, billions of years ago, was a geologically active world. It had volcanic systems, hydrothermal vents on the floors of its oceans and lakes. These environments are known to drive complex organic chemistry without any biology involved. Serpentinization reactions, Fischer-Tropsch synthesis, abiotic carbon fixation. The molecules found in Gale Crater could be the preserved remnants of that ancient geological chemistry, locked inside shielded rock for 3 billion years. Under this theory, Mars was never alive, but it was chemically rich, in ways we are only beginning to understand. Theory 2. Delivery from space. Carbonaceous meteorites, some of the oldest objects in the solar system, carry complex organic molecules. They rain down on every rocky planet. Many of the molecule types found in this Martian sample are also found in meteorites. Under this theory, the organics in Gale Crater were delivered from outside the Mars system entirely, absorbed into ancient lake sediment, and preserved. No biology required, just the endless background rain of cosmic chemistry that touches every body in the solar system. Theory 3, the one nobody says out loud first, but everyone is thinking. Biosignatures, the chemical remnants of living organisms, not life today. Mars almost certainly has no active surface life now, but life from the ancient past, when Mars had liquid water, a thicker atmosphere, and conditions that looked remarkably similar to early Earth. Under this theory, what curiosity found is a ghost, a chemical shadow left behind by microbes that lived in that lake 3.5 billion years ago, and died when Mars lost its ocean and its sky. Here is the uncomfortable truth. The current data cannot rule any of these out. The chemical signatures are consistent with biology. They are also consistent with geology. They are also consistent with meteoritic delivery. To distinguish between them, you need to measure something called the isotopic ratios of the carbon in these molecules. Life is chemically selective. Living organisms preferentially absorb lighter isotopes of carbon, carbon-12, over heavier ones. This creates a distinctive isotopic signature that persists in organic residues for billions of years. If the carbon in these Martian molecules has that same biological fractionation pattern, the implications are staggering. Curiosity does not have the instruments to measure isotopic ratios at that precision. The mission that can, Mars Sample Return, the joint NASA and ESA program designed to physically retrieve Martian rock samples and bring them back to Earth, where the full power of modern analytical chemistry can finally answer the question that has driven planetary science for a century. Mars Sample Return was designed for exactly this kind of moment, and now that scientists have identified precisely which rock type to target, which ancient lakebed layer, which preserved chemistry to seek out, the mission has a specific quarry. Not random surface rocks, not atmospheric dust, ancient shielded sediment from the bottom of a 3 billion-year-old lake that has already revealed it contains something that should not be there. Those molecules sat undisturbed inside Martian rock for over 3 billion years, through the death of a planet's ocean, through the loss of its atmosphere, through the long, cold silence of deep time. And then, a 6-wheeled robot the size of a car drilled through the surface and found them. Whatever they are, geological, cosmic, or the shadows of ancient life, they are the most complex chemical story Mars has ever told us, and we are only just learning to read it. If this is your kind of science, hit subscribe. We post every week.